Thank you very much. Please excuse me for sitting, I'm very old. Well, the topic discussed is one which is, in a certain sense, very peculiar, because it's very old. Roughness is part of human life forever and forever, and ancient authors have written about it. It was very much uncontrollable, and in a certain sense, it seemed to be the extreme of complexity, just a mess, a mess, and a mess. There are many different kinds of mess. Now, in fact, by complete fluke, I got involved many years ago in the study of this form of complexity, and to my utter amazement, I found traces, very strong traces, I must say, of order in that roughness. And so today I would like to present to you a few examples of what this represents. I prefer the word roughness to the word irregularity, because irregularity, to somebody who had had Latin in my long past use, means the contrary of regularity. But it is not so. Regularity is a contrary of roughness, because the basic aspect of the world is very rough. So let me show you a few objects, some of them artificial, others of them very real in a certain sense. And now this is very real. It's a cauliflower. Now, why do I show a cauliflower, a very ordinary and ancient vegetable? Because ordinary and ancient as it may be, it's very complicated. And it's very simple, both in the same time. If you try to weigh it, of course, it's very easy to weigh it, and when you eat it, then the weight matters. But suppose you try to measure its surface. Well, it's very interesting. If you cut with a sharp knife one of the florets of a cauliflower and look at it separately, you think it's a whole cauliflower, but smaller. And then you cut again, and you still get smaller cauliflowers. So the experience of humanity has always been that there are some shapes which have this peculiar property that each part is like the whole, but smaller. Now, what did humanity do with that? Very, very little. So, what I did actually is to study this problem and found something quite surprising, that one can measure roughness by a number. 2.3, 1.2, and sometimes much more. One day, a friend of mine, to bug me, brought a picture and said, what is the roughness of this curve? I said, well, just short of 1.5. It was 1.48. Now, it didn't take any time. I've been looking at these things for so long, so these numbers are the numbers which denote the roughness of these surfaces. I hasten to say that these surfaces are completely artificial. They were done on a computer, and the only input is a number, and that number is roughness. And so on the left, I took the roughness copied from many landscapes. To the right, I took higher roughness. So the eye, after a while, can distinguish these two very well. Humanity had to learn about measuring roughness. This is very rough, and this is sort of smooth, and this is perfectly smooth. Very few things are very smooth. So if you try to ask questions, what surface of a cauliflower? Well, you measure and measure and measure. Each time you look closer, it gets bigger, down to very, very small distances. What's the length or coastline of these lakes? The closer you measure, the longer it is. The concept of length of coastline, which seems to be so natural because it's given in many places, is in fact complete fallacy. There is no such thing. You must do it differently. What good is that to know these things? Well, surprisingly enough, it's good in many ways. To begin with, the artificial landscapes, which I invented, sort of, are used in cinema all the time. When you see mountains in distance, they may be mountains, but they may be just a formula, just cranked on. Now it's very easy to do. It used to be very time-consuming, but now it's nothing. Now look at that. That's a real lung. Now, a lung is something very strange. If you take this thing, you know very well, it weighs very little. The volume of a lung is very small. But what about the area of the lung? anatomists were arguing very much about that. Some said that normal males' lung has an area inside of a basketball, and the others said no, 5 basketballs. Enormous disagreements. Why so? Because in fact, the area of the lung is something very ill-defined. The bronchi branch, and they branch not because, and they stop branching not because of any matter of principle, but because of physical consideration, the mucus which is in the lung. So what happens is that a whale will have a much bigger lung, but if it branches and branches down to distances about the same for a whale, for man, and for a little rodent. So now what good is it to have that? Well, surprisingly enough, amazingly enough, the anatomists had a very poor idea of the structure of the lung until very recently. And I think that my mathematics, surprisingly enough, has been of great help to the surgeons studying lung illnesses and also kidney illnesses. All these branching systems for which there was no geometry. So I found myself, in other words, constructing a geometry of things which had no geometry. And the surprising aspect of it is that very often the rules of this geometry are extremely short. You have formulas that long, and then you crank it several times, sometimes repeatedly, again, the same repetition. And at the end, you get things like that. This cloud is completely 100% artificial. Well, 99.9. And the only part which is natural is a number, the roughness of the cloud, which is taken from nature. Something so complicated, a cloud, so unstable, so varying, should have a simple rule behind it. Now, this simple rule is not an explanation of clouds. And the theory of clouds had to take account of it. I don't know how much I've advanced. This picture is rather old. I was very much involved in it, but then turned my attention to other phenomena. Now, here is another thing which is rather interesting. One of the shattering events in the history of mathematics, which is not appreciated by many people, occurred about 130 years ago, 145 years ago. Mathematicians began to create shapes that didn't exist. Mathematicians got into self-praise to an extent which was absolutely amazing, that man can invent things that nature did not know. In particular, it could invent things like a curve which fills the plane. A curve is a curve, a plane is a plane, the two won't mix. Well, they do mix. A man named Peano did find such curves, and it became an object of extraordinary interest. It's very important, but mostly interest because a kind of break, a separation between the mathematics coming from reality on the one hand, and new mathematics coming from pure man's mind. Well, I was very sorry to point out that the pure man's mind has, in fact, seen at long last what had been seen for a long time. And so here I introduced something, the set of rivers of a plane filling curve, and well, it's a story unto itself. So it was in 1875, 1825, an extraordinary period in which mathematics prepared itself to break out from the world. And the objects which were used as examples when I was a child and a student, as examples of the break between mathematics and visible reality, those objects, I turned them completely around. I used them for describing some of the aspects of the complexity of nature. Well, a man named Hausdorff in 1919 introduced a number which was just a mathematical joke, and I found that this number was a good measurement of roughness. When I first told it to my friends in mathematics, they said, "Oh, don't be silly. It's just something." Well, actually, I was not silly. Great painter Hokusai knew it very well. The things on the ground are algae. He did not know the mathematics. It didn't yet exist. And he was Japanese who didn't have no contact with the West. But painting for a long time had a fractal side. I could speak of that for a long time. The Eiffel Tower has a fractal aspect. And I read the book that Mr. Eiffel wrote about his tower, and indeed it was astonishing how much he understood. This is a mess, Brian loop. One day I decided, halfway through my career, I was helped by so many things in my work, I decided to test myself. Could I just look at something which everybody had been looking at for a long time and find something geometrically new? Well, so I looked at this thing which is called Brownian motion, which just goes around. I played with it for a while, then I made it return to the origin. Then I was telling my assistant, I don't see anything, can you paint it? So he painted it, which means that he put everything inside. When this thing came out, I said, stop, stop, stop. I see it's an island. And then, amazing, so Brownian motion, which happens to have roughness of number of 2, goes around. I measured it, 1.33, again, long measurements, big Brownian motions, 1.33. Mathematical problem, how to prove it? It took my friends 20 years. 3 of them were having incomplete proofs. They got together, and together they had a proof. So they got a big medal in mathematics, one of the 3 medals that people received for proving things which I've seen without being able to prove them. Now, everybody had asked me at one point or another, how did it all start? What got you in that strange business? What got you to be, at the same time, a mechanical engineer, a geographer, and a mathematician, and so on, and a physicist? Well, actually, I started, oddly enough, studying stock market prices. And so here I had developed this theory, and I wrote books about it. Financial prices increments. To the left, you see data over a long period. To the right, on top, you see a theory which is very, very fashionable, because it's very easy, and you can write many books very fast about it. So there are thousands of books on that. Now, compare that with the real price increments. And where are real price increments? Well, these other lines include some real price increments and some forgeries which I did. So the idea there was that one must be able to how to say, model price variation. And it went extremely well 50 years ago. For 50 years, people were sort of poo-pooing because they could do it much easier. But I tell you, at this point, people listened to me. These 2 curves are averages, Standard & Poor, the blue one, and the red one is Standard & Poor, from which the 5 biggest discontinuities are taken out. Now, discontinuities are a nuisance, so in all of many studies of prices, one puts them aside, well, acts of God, and you have the little nonsense which is left. The acts of God on this picture are 5 acts of God are as important as everything else. In other words, it is not acts of God which we can put aside. That is the meat, the problem. If you master these, you master price, and if you don't master this, you can master the little noise as well as you can, but it's not important. Well, here are the curves for it. Now I get to the final thing, which is the set to which my name attached. In a way, it's the story of my life. My adolescence was spent during German occupation of France, and since I thought that I may vanish within a day or the week, I had very big dreams. And after the war, I saw an uncle again. My uncle was a very prominent mathematician, and he told me, look, there's a problem which I could not solve 25 years ago, and which nobody can solve. This is construction of a man named Julia and Nam Fatou. If you could find something new, anything, you will get your career made. Very simple. So I looked, and like the thousands of people I tried before, I found nothing. But then the computer came, and I decided to apply computer not to new problems in mathematics, like this wiggle, that was a new problem, but to old problems. And went from what's called real numbers, which is points on a line, to imaginary complex numbers, which are points in the plane, which is what one should do there. And this shape came out. This shape is of an extraordinary complication. The equation is written there. Z goes into z squared plus c. It's so simple, it's so dry, it's so uninteresting. Now you turn the crank once, twice. Marvels come out. I mean, this comes out. I don't want to explain these things. This comes out. this comes out. Shapes which are of such complication, such harmony, and such beauty. This comes out repeatedly again, again, again. And that was one of my major discoveries, to find that these islands were the same as the whole big thing, more or less. And then you get these extraordinary Baroque decoration all over the place. All that from this little formula, which has whatever, 5 symbols in it. And then this one, the color was added for 2 reasons. First of all, because these shapes are so complicated that one couldn't make any sense of the numbers. And if you plot them, you must choose some system. And so my principle has been to always present these shapes with different colorings, because some colorings emphasize that, and others emphasize that, and other that. It's so complicated. In 1990, I was in Cambridge, UK, to receive a prize from the university, and a few days later, a pilot was flying over the landscape and found this thing. So where did it come from? Obviously from extraterrestrials. So the newspaper in Cambridge published an article about that discovery and received the next day 5,000 letters from people saying, but that's simply a Mandelbrot set, very big. Well, let me finish. This shape here just came out of an exercise in pure mathematics. Bottomless wonders spring from simple rules which are repeated without end. Thank you very much.